So we now move on to the next presentation. So I call Alberto. So Alberto is going to talk about COLIBRI, this CERN-wide common course library. So Roberto Perro is a PhD student in physics at the Aix-Marseille University in France, working on the LHCb experiments at CERN. He's a member of the online project where he works on validation and verification of FPGA gateware for high-throughput data acquisition system. So please, Alberto, the floor is yours.
Okay. Good afternoon, everybody. Today I will talk about the work on COLIBRI, which is our effort to have a common core library CERN-wide. So just a brief overlook. I will explain our current situation and what motivated us to work on this library, how we structured it and the philosophy behind it, the content, the most important part, which is validation and verification, the coding guidelines, and how we put into practice all of this work with the case studies. So to start, I will talk about the LHCb experiment here at CERN. In the LHCb experiment, we use a common hardware platform, which is the PCI 40 here in the figure. And a common framework, common gateway framework is shared between all of the subdetectors to reduce the development overhead. But subdetectors still have to develop their own custom gateware to do the processing of the data coming from the front end. This results in around 30 different gateway variants, which are very difficult to test and maintain, as you can imagine. And also, as most of FPGA design, this is not very portable gateware between even devices of the same vendors, let alone different vendors. On the validation side, the test coverage is very limited, and the test benches are only useful on a small amount of cases. And we use custom TCO scripting that only can run on one simulator, and sometimes even only on a specific version. And also, simulation takes a long time, like 3 hours for a single gateway flavor. So you can imagine that we cannot, 30 by 3, it's a lot of time. So we would like to run them in parallel, but this will require for each instance a license, which will cost a lot. So the motivation was to start an effort on modern validation and verification methodologies. And this showed us that we need obviously better and more exhaustive integrated testing. And also most of the modules we have in our gateware use proprietary code. So this limits a lot the selection of tools and portability on new platforms. A bunch of entities are also similar functionality, but they're written by hand by different developers. So this will hide corner case bugs, and we have duplication in our code base. Also, it's very important that we are going through an upgrade of the data acquisition system. And this upgrade will require higher data throughput, which will require a new hardware platform. So we will have to move from the current one, which is the PCI 40, to the PCI 400. And this will require a major porting effort in the current gateware. And even though we are using the same vendor, which is still Altera, from one generation, which is ARIA, to Agilex. So we decided that to ease up and speed up the development part, we needed a common library, which is called COLIBRI. So let's talk about the structure and the philosophy behind it. Obviously, the library has 3 foundation principles. It has to be open source. Right now it's under GPL v3, but thanks to Javier, probably we will change it. We have a completely independent library to ensure the portability and avoid the vendor lock-in. And also, all of the components must be validated and verified to ensure the correct functionality to the user. And these principles are translated into practice into the whole library written in a subset of VHDL 2008, which is compatible with all of the toolchain you see there. We tasted it. The choice of a single language also enables us to use open source simulators such as VHDL, thanks to Princeton, and NVC. And also open source simulators and modern testing frameworks such as UVVM, OSVVM, and VUnit can run in CI/CD in parallel without requiring licensing. Also, well, since it's a modern world, we are using Python-based scripting frameworks such as VUnit, and we are discouraging the use of TickleScript as far as we can. The library content is a collection of the most common cores we encounter during the design and simulation of gateware, and they have all been written from scratch, this to ensure the uniformity and the functionality. And also, we are still contributing to this library, so it's an ongoing project. The main categories, as you can see, we have from the common function, which are just math functions, to memory entities, to interfaces, and more. The validation and verification part is the most important part, and the first part is the test benches. We are adding test benches for each component available in Colibri, and they are self-checking test benches, which are run in CI, using also the VUnit testing framework, which enhances the portability and makes it easy to change simulators from proprietary ones to open source ones. Also, we use UVVM and OSVVM for the BFMs, for the random stimuli and scoreboards, so we can improve the test functionality. And in CI, we use the NVC simulator, which is very fast and very stable. The other important part in verification and validation is formal verification. I don't know if you are familiar with these techniques, but formal verification is basically a mathematical proof of correctness of the behavior of the gateware. And this formal verification test can guarantee the absence of bugs, mathematically proving that a model satisfies its requirements. So the library components, which can be formally proven, are equipped with formal verification tests. And these tests are also run in CI, using VHDL as the VHDL interpreter, Yosys as the synthesis engine, and Symbiosis as the formal verification frontend, which are all open source tools. So as I introduced, we use a lot the continuous integration, and this will guarantee the functionality of the library completely. We use containers in GitLab runners. Right now it's hosted on gitlab.cern.ch, running self-checking test benches, the style checking, and the formal verification. And both the test benches and the style checking have also automated pipeline reports using XML reporting. So this makes it very easy for developers to spot the bugs and which tests have failed. Last but not least, the coding guidelines are included in the project. So to contribute and to guarantee the uniformity of the code base, we have an enforcement of guidelines in CI using the open source linter and style checker VSG. And obviously, well-commented code, markdown documentation, and diagrams are also a crucial part for the wide adoption of Colibri. Okay, let's go from the theoretical part to the application on the field, and let's take a look at some case studies. So the first case is the development of the Aurora protocol. Aurora is an open source protocol supported by AMD Xilinx devices, and it will be used in the fast-reach front-end ASIC in the reach subdetector of the LHCb experiment, which will send data encoded in Aurora over an LPGBT link. The decoding of the protocol will run on the backend FPGAs and has been entirely developed using Colibri. And the FPGA gateware has been tested first on Xilinx, you can see in the picture Zinc UltraScape Plus, and also on Altera, which is our main gateware board. The porting effort only required setting the right timing and physical constraints. So second case is a 10G UDP IP transmitter. So as part of the EP R&D work package 9.3 and the ECFA detector R&D 7.5, we are evaluating Ethernet as a front-end data link. And part of this work is a proof of concept for a media converter between LPGBT and Ethernet. And this media converter was designed as a full UDP IP TX pipeline using only Colibri components. And this code was ported and tested successfully on both AMD, Xilinx, and Microsemi FPGAs, thanks to the EPA as a contribution. The last case, it's more on the simulation side. we used and we applied formal verification to find some gateware bugs in our LHCb repo, and they showed up during commissioning. It was very hard to find corner cases. So since most of the components used in the gateware are proprietary, we have to replace them because they are not compatible with the open source formal verification toolchains. And we put COLIBRI components in place, which are formally proven, so we know that they behave as they have to. And this also helped us to use open source simulators also for the entire gateware to extend the test coverage. Last, we tested the portability of the library with a simple gateware consisting of serial readout of a sensor, some FIFOs, data buffers, and UARTs to simulate a very simple front-end readout. And this was ported with success on very low power, low cost FPGAs such as Lattice, Efinix, and GoWin. So this talk and this work presented wants to be a step towards a CERN-wide common core library. And the structure was thought to have a very easy adoption, portability, and integration. The LHCb developers will widely use COLIBRI to develop the gateware for the next upgrade. And also, this library is also being included in the EPR&D working package 9.3.1 firmware portability framework. And we hope that more experiments and groups will join us in this venture and adopt COLIBRI for the developments. Thanks for the attention.
Thank you, Alberto. Questions? Yeah, already one in front.
First of all, thanks for your talk. It was very interesting. I'm just wondering, why GPL B3? Because, I mean, okay, if you want to basically extend the scope of the library to be used, for instance, in the industry, basically, it will be difficult to adopt. Because, you know, like, okay, you can, companies that basically are based on services basically cannot use this library because probably the other company that is paying there and them basically is okay. No, I want this proprietary. Yeah.
So the choice of the license. Thanks for the question. For now, it was just a sort of placeholder because it's still under CERN EP R&D work group. So when we are not publishing it yet, so it's available inside CERN. Throughout all of the experiments, but it's not yet to the public, so we didn't discuss much on the license itself, and I'm pretty sure we're going to change it with the open hardware, CERN open hardware license. Yeah.
Thanks for your presentation. Just a question about you cited that you have developed the UDP IP block based on the COLIBRI library. And how have you managed to work with a proprietary, or you have completely substituted the proprietary Ethernet MAC and physical layer, or you have reinvented or rewritten the IP, or you rely on the vendor?
So for now, thanks for the question. We rely on the vendor implementation. So it's only the UDP and IP stack that has been developed with COLIBRI, and then it's just an AXI stream interface to the vendor Mac.
So yeah, thank you for the talk. I have a similar question for the simulation side. So some of the unavoidable proprietary blocks, the hard IP, like the transceivers, the vendors, they give models which are encrypted and with the keys only available to proprietary commercial vendors of simulators. What's your approach to simulate that? Do you avoid those blocks, or do you have alternative, simpler models that you develop? What do you do about this inability of open source simulators to simulate these blocks?
So, for example, talking about the LHCb gateware we designed, we obviously used some QSys components, which is the IP blocks from Altera. And we have some replacements for those blocks for just removing them from the simulation to use them with open source simulators. But it's not the point of the library to have to use, for sure, I mean, open source simulators. The library itself, since it's open source, uses open source simulators. But you can plug it in every proprietary simulator, and it works as it should. So you can use Riviera or whatever you prefer.
So related to this question, the test bench are mostly written in VHDL.
It's all written in VHDL, the whole library and
the library and the test benches.
And the test benches, yes. It's and also, I mean, the formal verification also uses what is called PSL, which is a subset of VHDL for formal verification. So it's the equivalent of system verification parts, but for VHDL.
Any other question?
Thank you. A couple of curiosities. The first is, how much is difficult to port some kind of present design into Colibri?
It depends on what you need to put in. So it is
to have some kind of compatibility for your with your rules of design.
Oh, so for us, it's actually quite, I mean, it should be quite simple. So you have only to check that what is your interface. So you just take whatever is your entity you want to substitute and put our entity in. Obviously, some of the entities have already like diagrams on explain how the various signals like ready, valid, handshakes works, but it should be quite easy to put it. Just remove the old entity and put the Colibri one.
Okay, but you have to not have any check on the let me say styling code of VHDL of the model or stuff like this in principle.
If you put if you put it in your work,
but in principle you can put inside your library without any.
Yeah, you just import it.
Other curiosity, do you have also the UDP RX blocks?
We are developing it. Yeah, not yet, but yeah.
Anyone else?
I have a question myself. So when the day comes that you really distribute this, and
yes,
hopefully plenty of people will use it,
yeah,
they will find bugs.
I hope so.
How are you prepared to handle that?
So, well, we have to cover more with the test benches. So that's the most important part. We're trying to be as exhaustive as possible. We're just basically, I would say that 10% is coding the entity and the rest is just 90% of the work is doing test benches and formal verification. We're trying to do it the best, but obviously issue tracking, merge requests are all obviously welcome for this kind of stuff to add features and also to debug.
So you plan to have issue openable by the user, and then
yes,
you will. Okay.
Yes.
Thank you.
Last chance for a question. Maybe out of curiosity, how many people are working on this project?
So right now we are 2. Yeah, well, I was the main developer that started last year, and now I have a student that is working with it.
Great.
Yeah. Thanks.
Congrats. Let's thank Alberto again.